Hello everyone. In this video, we will go over how to do numerical integration in Python. I'll go over the basic numerical integration techniques like trapezoidal rule and Simpson's one-third rule. We'll go over an example and I'll also show you how to do an integration on SymPy. And then we'll cover how to do this in a multiple application format. Okay, so let's get started. So first thing first, we'll start with the example, the polynomial equation given here. You can write it as a lambda function, okay, and you can compute it at any point, f of 3 for example. To integrate this, you can use NumPy packages trapezoidal rule, so import NumPy as NP, and you can just apply this across limits. So let's say a equal to 0, b equal to 0.6. Then you can create the x points a and b, and the y points are going to be f of a and f of b, and np dot traps of x, y comma x. Okay, so this numerically you can find it using the NumPy package. You could also do it using the SymPy symbolic package. So import SymPy as sp, and then you could recreate this equation, but you can have x as a symbolic variable. So sp dot symbol x. So this is what x looks like, and you could recreate your function not as a lambda function but as a symbolic function. So you can just remove lambda from here. Now this x in this equation is going to be the symbolic x, and you can see the output here as shown here. To integrate it, you can just say f dot integrate, and this will give you the symbolic integration of that equation. To evaluate it at a particular point, you have to use tuple. The first input is going to be the variable that you will set the limits for, so that's going to be x, and then the limits. So the limits are a and b. Okay, so this will give you a different result. Okay, and this will be the more accurate one. Okay, because this is done analytically. Okay, so you can find analytical solution for known functions, so functions that can be integrated or differentiated, and you can use the symbolic package to do so. Okay, now let's see how you can do a single application of trapezoidal rule. So let me make a plot to show you how the function looks like, and then we'll see how trapezoidal function works. So import matplotlib.pyplot as plt. So this is the plotting package that we're going to use, and let's have a look at it. Let's plot the function. Okay, I'm going to use the lambda function again over here, and x, I'll create a range of values for x between a and b at some arbitrary small step size, and my y will be a evaluation of the function at these values. Okay, then you can just say plt dot plot x comma y. So that's the function that you have, and applying the single application is like drawing a trapezoidal from a to b and then finding the area of that trapezoid. So something like this. So you take a and b, you draw a straight line between them, and then you find the area under the curve. So in this particular case, this is the 0 axis, so it's going to be a bit of area under the curve like this. Okay, now you can see if you apply a single application, this is not going to be accurate because you're not capturing this area, you're overestimating these areas. Okay, but let's see how the implementation is. So to visualize this, I will use the plt.area fill between function, and then give it the x values, which are a and b, and the y values, which are f of a and f of b. Okay, so you can consider this to be your single application of trapezoidal. So I'm going to put this as a function, single trapezoidal. Okay, So given the function and the limits, this is what visually the trapezoidal rule is doing. Okay, so I can call my function. Okay, just to make it transparent, I'll set the alpha value. Okay, so this is what's happening. To numerically find this, you just have to evaluate the function using this equation. So this is the equation b minus a f of a plus f of b divided by 2. So your I value is going to be equal to b minus a multiplied by f of a plus f of b, the whole thing divided by 2. Okay, and you can just return I. And if you run this and print I, this is the number that you get, and it should be exactly the same number that we found using the NumPy trapezoidal function, which is the case over here. Good. Now, if you had to apply this multiple times, the way to do that would be to break your points into multiple segments, and then apply in the integral using trapezoidal rule at each stage, and then finally to add all of them up. Okay, if you add all of them up, you get the total integration of the area under the curve. Okay, so let's try to attempt to do this. So to do this, let's first make a for loop for I in range up to some value n. So we have n segments. This is the number of segments, let's say 10. And during this, what we will do is we can repeatedly call our single trapezoidal rule. So single trapezoidal rule, and we'll store the result in the value I. Okay, and the total I total will start with a value of 0, and after calculating I, you can then add it to the total. So I underscore total equal to I underscore total plus I. So every time this loop goes through each segment, it finds the integral of that segment and then adds it to the total. Okay, so the final total should be close to the right answer. Okay, so if I try to do this, if I run this, you will see that it's basically doing this 10 times. It's calculating the value from A to B 10 times, which is not what we want. We want it to do this for segments. Okay, so instead of saying A and B, which are the actual limits, I'm going to call this an intermediate variable A0 and B0. Okay, what we want is now to have A0 here, and let's say you're dividing it to 10 segments or however many segments, then this value should be B0. Okay, so that will be when I equal to 1, I equal to 0. And for the first iteration, you do the integration here. Okay, after that, you do the integration between this becomes your A0, then this becomes your B0. Okay, after you integrate that, this becomes A0, this becomes B0, and so on. Okay, so for that, the first one is easy. The first one is A0 equal to A. That's where it starts. And you also need to know the width of your sub intervals or your segments. So H is going to be equal to B minus A divided by N. Therefore, B0 is going to be equal to A0 plus the segment width. Okay, now let's see if this works. Let me plot the function so you can also see what the function looks like. So you can see this is taking the beginning portion of it, so it's kind of working. So this is A0, this is B0, but instead of doing it 10 times across, it's only doing it 10 times here. So your result will not be correct. Okay, you can actually look at the value for I total. Yes, you can see that it's not correct. It should have been closer to this number. This was the true value, right? So something is wrong. So the way to fix this is you need to move your interval, or you need to move on to the next segment when the loop goes forward. Okay. To do this, it's easy. You can just say that your next A0 is going to be your previous B0. So after you compute your integral, you can now reset your A0 to become B0. Okay. So if I run this, it still doesn't work. The reason for this is that B0 is updated outside the loop. B0 should be updated inside the loop, not outside. So we have to calculate this right here. Okay, so A0 is A, then B0 is A plus H, so that's this point. And then after you're done computing your single trapezoidal rule, your new A0 is going to be the new A0. This is going to be A0, which happens to be the B0 for the old segment. Okay, then when the loop continues, the new B0 is calculated with respect to A0 plus H and so on. So let's see if this works now. Okay, there you go. So you can see it has broken it down into segments, and you are much closer. So 0.954, you're much closer to the true value, 0.963. Okay. So this is how you do numerical methods in Python. And to do Simpson's 1/3 rule, for example, you can just come back to the single trapezoidal rule and make another one. For example, single Simpson 1/3. It's the same inputs, but the formula will change. It's going to be f of x0 plus f of x1 plus f of x2. X1 has a factor of 4, and it's going to be divided by 6. Okay, now you need to know what is x0 and x1. X0 is easy, it's the first boundary. X1 is equal to, now you have, when you do Simpson's 1/3, every segment that you have, let's say the original program, the multiple application is going to split it up into one segment. Within that segment, you will then break it down into another 2 segments and then apply Simpson's 1/3 rule on it. Okay, if you're doing 3/8, this would have become 3 segments. Okay, so keep this in mind. So there is a height associated with the first one. This is h, which comes from the multiple application. Okay, but inside the function you will have another h which is specific to the method. Okay, so here I'm going to do another h specific to the method. So here h is going to be equal to b minus a divided by 2. Okay, so in Simpson's 1/3, you're dividing the interval into 2 segments, so that your h is going to be b minus a over 2. Okay, if you were doing 3/8, this would be different. So x0 is a, x1 is x0 plus h, and x2 is x1 plus h. Okay, and that's your Simpson's 1/3 rule. So you can run this, and you could try the multiple application with Simpson's 1/3. Just change trapezoid to Simpson's 1/3 and run, and you should get a much more accurate result, 0.96. Okay, I hope it's clear. Thank you.